If you look closely at the rigid lines and mechanical keys of this plastic chassis, you are looking at a perfect slice of cassette futurism. Launched in France in 1982, the Minitel was designed to sit neatly next to a standard telephone. To solve the problem of getting people to actually adopt a new network, the French state bypassed the market entirely and gave millions of these terminals away for free. The state-run network that powered these machines was completely shut down in 2012. The original servers are gone, yet today these physical terminals are experiencing a massive resurgence among hardware hackers. Makers are actively wiring these legacy CRT displays into modern microcontrollers, hooking them directly to Arduinos, ESP32s, and Raspberry Pis. They aren't gutting the machines or replacing the internals. They are driving modern silicone through specific, highly resilient electrical interfaces built into the original 1980s design. Directly on the back of most units is the physical connection point, a standard 5-pin DIN socket functioning as a serial port. This graph plots a standard RS-232 serial signal. The communication relies on high bipolar voltage ranges, aggressively swinging between negative and positive 15 volts to transmit data. That massive electrical range presents a strict physical barrier for modern microcontrollers, which operate tightly at either 3.3 volt or 5 volt logic. Sending an unmitigated 15 volt RS-232 swing directly into a modern processor instantly destroys the silicon. The workaround routes that signal through a level-shifting Max 232 chip, taking the hit and compressing the high voltage into a safe, flat wave. The Minitel offers a built-in engineering loophole. Its serial port does not use RS-232 at all. It natively outputs a flat 0 to 5 volt TTL logic level. That 5 volt maximum precisely matches the electrical input limits of development boards, like an ESP32 or an Arduino Mega 2560. Because the terminal outputs strict 5 volt TTL logic, makers can run wires from the 1980s serial pins straight into modern hardware UART pins, completely bypassing the need for any intermediate level-shifting circuitry. To understand why this makes it such a capable modern peripheral, we have to look at the dumb terminal architecture. The manufacturer purposefully omitted local processing memory and storage from the hardware to minimize manufacturing costs. The terminal couldn't compute anything locally. It relied entirely on querying centralized databases housed deep within the French state's X.25 packet switching network. To physically reach those databases, the machine routed its data over standard analog telephone lines. Bridging the digital terminal to the analog phone line required a specific modem protocol, known as the ITU V23 standard. Look at this network topology map. The V23 protocol was highly asymmetric, starting with a severely throttled uplink speed. Data traveled out of the terminal at exactly 75 bits per second. That tiny bandwidth was mathematically calculated to be just fast enough to register individual human keystrokes from the tactile AZRT keyboard. The return path from the network handled much more volume. Data flowed back down to the terminal at 1200 bits per second. That downlink was optimized specifically so the machine could pull down text and basic graphical instructions, rendering them line by line onto the CRT display. Wiring a Wi-Fi-enabled ESP32 into that rear 5-volt TTL port completely isolates and bypasses the internal V23 analog modem. Routing around those analog bottlenecks means developers can inject data directly into the display logic at full hardware speed, effectively hijacking the screen to show modern server outputs. To make those server outputs readable, you have to navigate the hardware's inherent display language, video text encoding. This screen displays a variant of the alpha-mosaic Teletel standard, mapping exactly 40 columns and 25 rows. The grid constructs images out of blocky, low-resolution character cells. This rigid matrix allowed the efficient transmission of primitive consumer graphics, packing visual data tight enough to squeeze through that slow 1200 bit per second downlink. While video text was highly efficient for consumer interfaces in the 1980s, a 40-column width is mathematically insufficient to render a modern command line interface. Try to push text-dense output into this mode, and the string logic will immediately break and wrap around the screen. To fix that layout limitation, engineers utilize a dual-mode logic feature integrated during the manufacturing of the later Minitel 1B models. By typing a precise physical hardware trigger on the keyboard, holding Function plus T and then pressing A, you execute a mode switch. The display immediately shifts, compressing the 40-column mosaic blocks and doubling the density to create a purely text-based 80-column layout. That 80-column mode conforms exactly to the international VT100 telecommuting standard. The final requirement is to synchronize the software timing. Pressing Function, P, and then 4 pushes the serial baud rate up to 4800 to handle modern data output speeds. By locking into VT100 mode and jumping to 4800 baud, the terminal abandons its proprietary French graphical protocols. It now speaks the universal text-based language of global server administration. This stack allows you to use these units as dedicated Linux shells for a Raspberry Pi, wire them to an Arduino to run a micro version of Lisp, or dial into simulated Teletel bulletin boards over modern Wi-Fi. Operating them today does not require destructive circuitry hacks. The applications rely entirely on the factory hardware stack, native 5-volt TTL logic, internal VT100 formatting, and adjustable serial baud rates. For a software engineer, a dumb terminal provides a highly specific environment. You type on a machine entirely devoid of background operating system processes, local memory management, or modern user interface bloat. The Minitel remains relevant in the 21st century because its highly constrained, brutally efficient input-output architecture precisely anticipated the direct hardware interfacing requirements of modern microcomputing.